another area that we will be using curved arrows a lot, and you'll see movement of electrons deals with resonance. So as a reminder, resonance occurs when you have molecules containing delocalized electrons, electrons that are not sitting in one place, they're moving between elements. This means that they have multiple Lewis structural representations, and those representations are called resonance structures. So we're going to see different representations of the same molecule to kind of show you places where the electrons sit. So here's an example. Protonated formaldehyde actually has two important resonance forms. So you can see one of the resonance forms has a single bond between the carbon and the oxygen. And the oxygen contains two lone pairs, and it's forming two bonds, one with carbon, one with hydrogen. And the carbon itself has a formal charge, a formal +1 charge on it. One other form could be when the electrons move from the oxygen, one of the lone pairs moves from the oxygen to form a second bond. So we're forming a pi bond, making a double bond between the carbon and the oxygen. When this happens, be reminded of formal charges. And if you don't remember how to calculate formal charges, go back to the review video. The oxygen is now forming three bonds. That gives it a formal charge of +1. And you can see that the electrons have moved in to form this double bond between the carbon and oxygen. So this compound doesn't really convert between A and B. In reality, it's actually kind of a weighted sum of the two structures. It's actually half and half A and B mostly during the time. So ultimately, it has kind of a partial positive charge on carbon and a partial positive charge on oxygen. So you don't ever have a full-blown positive on carbon or a full-blown positive on the oxygen. This is a true resonance structure in which you're sharing the electrons equally between these two forms. But when we show it, when we want to show the forms, we have to draw them in these structures as shown above, A and B. And again, using our curved arrows to imply how the electrons are moving to get between A and B. Another example, again, here's a Lewis structure of ozone. And if you look at the Lewis structure, it suggests that two of the OO bonds, the oxygen bonds, are not equivalent. Here we see an oxygen and an oxygen with a double bond, and here we see an oxygen and oxygen with a single bond. But experimentally, we confirmed that they're all equivalent to each other. They actually have the same length between each other, and the outer oxygens have the same partial negative charge. We don't have one oxygen with a negative charge and one with a positive and one with a neutral. Instead, we actually see an oxygen in the middle with a positive and the two outer ones having kind of this half negative. And the way that this can happen, we showed this experimentally, but the only way that this actually can exist is due to resonance. So we know that these electrons don't ever just sit in one place. They're moving constantly between the oxygens. And again, the resonance represents the delocalization and stabilization of the charge. This is the key thing. We know if you have resonance, you actually have more stabilization of that charge. So having just a full negative charge and a full positive charge on atoms like that is very unstable. But to share the load, to share the charge load is actually stable. And that's why compounds do this. So what are the rules of resonance? These are things I want you guys to make sure that you know and think about when you're drawing structures. we're going to be looking at some examples as well. Rule number one to be thinking about: when can resonance even be considered? That's the question a lot of people have when they're looking at this. Like, how do I know that there's even going to be resonance? When can it even be considered? So rule number one: the connectivity and position of the atoms must remain the same in all resonance structures. So if you're trying to draw resonance structures, elements must be in the same connection. So here's an example where we have structure A and B. These structures are not resonance structures. Here we tried to move a double bond, that's fine. The main thing that makes them different and would not be considered resonance is because a hydrogen has moved. See, this hydrogen is connected to an oxygen here, and it's connected to the nitrogen here. That is not allowed for resonance. Resonance is the same structure, but we're only moving electrons. In this case, we've actually formed an isomer because we've actually moved a connection of an atom from one atom to another. So these are not resonance structures, these are isomers. Rule number two to consider in resonance is that each contributing structure must have the same number of electrons and the same net charge. That's for the whole molecule. Ultimately, the whole molecule has to have the same net charge and, of course, the same number of electrons. We can't suddenly be adding or taking away electrons because that means we're actually doing a reaction. This isn't a reaction, this is just a restructuring of the electrons in the same molecule. So here again is an example, molecules A, C, and D. So A, C, and D are all resonance structures. They all have a net charge of 0. The starting structure, you can see it doesn't have any formal charges. Structure C has a positive and a negative charge, which ultimately cancels out to 0. Same with structure D, a positive and a negative charge, which cancels out to 0. So all of these are valid in that way. They have the same net charge. So even though the formal charges are on different atoms and they move around, that is okay as long as you go by this rule: same net charge and same number of electrons. Again, you can see via my curved arrows that electrons aren't going anywhere else. They're just moving between atoms in the molecule. Another rule to consider for resonance is that each contributing structure must have the same number of unpaired electrons. Here is our same example from before: A, C, and D. I showed you this on the last slide, and the movement of their electrons. You can see structure F here. We actually have moved electrons again, except in this case, there is one single electron on this carbon and one single electron on this oxygen. Well, first of all, we know that curved arrows only move paired electrons, but this also cannot be a resonance structure. F is not a important resonance structure of A because it doesn't have the same number of unpaired electrons. So there are two single unpaired electrons here, one on carbon, one on oxygen, instead of paired electrons that are moving between a carbon and oxygen or carbon and a nitrogen. Another rule to consider for resonance is that atoms of a second row element shouldn't violate the octet rule. This is just a simple rule you should always be looking for in your structures. So an example here, we have our structures G, H, and I. G and H are resonance structures, and you can see that the movement of electrons goes from this double bond here and then on to form a double bond here. This would be the ultimate movement of electrons. We moved our electrons from the double bond between the nitrogen and the oxygen, and then to the, ooh, excuse me, I actually moved these wrong. This is moving from this oxygen. We're taking our lone pair and moving them to form a double bond here. And then these electrons are moving up into this oxygen. I know that because if we look at our lone pair number here, you can see there are 2 here and 3 here. And this oxygen has 3 and started with 2. So again, here's the resonance structure between G and H, moving of electrons. However, if we look at structure I, you can see that nitrogen is forming 1, 2, 3, 4, 5 bonds, and it has no charge on it, which is incorrect. If you actually calculated the formal charge for this nitrogen, it would be an incorrect. This is incorrect. It should not be 0. And it is completely violating the octet rule. So it has the wrong formal charge. It's forming 5 bonds. Nitrogen can form 4 bonds with a positive charge. We know that. That is a valid form of it. Nitrogen also usually forms 3 bonds, but with a lone pair. So nitrogen can be in this structure, or it can be in this structure, but not in this structure, which is forming all 5 of these bonds. So this is just a simple violation of the octet rule, and in general would not be considered for resonance. So you talked about how when resonance can be considered, but we can also think about which resonance form is most important. So sometimes you will have multiple resonance forms, and some of them are going to be more stable or more important than others. One rule to think about in the importance of resonance structures is which resonance structure contains more covalent bonds. Those are typically in the more important structure. But so between our structures J and K, you can see that J has more covalent bonds. It has a double bond and 2 single bonds, whereas K has just 3 single bonds. So in this case, our major resonance form would be J, and the minor resonance form would be K. They're both valid forms. They both can be considered. It's just that J is the more important resonance form. Another rule to think about, these rule 5 and 6 kind of go hand in hand, but resonance structures with minimal separation of opposite charges are most important. So in L and M, you can see that L lacks any formal charges. There are no positive or negative charges on it, whereas M has a positive and a negative formal charge. The oxygen has a negative formal charge. One oxygen has a negative formal charge and the other has a positive formal charge. So in this case, the structure that does not have as many formal charges, this is the way you can think about it, minimal separation of opposite charges, is going to be the major resonance form. So this would be structure L versus structure M. Again, they are both contributing forms. They are both valid forms. It's just that L is going to be the more important structure. Another rule to think about to figure out the importance of structures is that resonance structures with negative charges on the more electronegative atom, so negative charge on the electronegative atom, the atom that likes to be negative, and a positive charge on the more electropositive atom, so the atom that likes to be positive, are the more important and major contributors. So here we have 2 forms. They have the same number of covalent bonds. They have the same charge. Both of them have a negative formal charge. The only difference is that in the resonance structure A, there is a negative charge on the oxygen. And on resonance structure B, there's a negative charge on the nitrogen. And if you remember from our periodic table, electronegativity is going to increase as you go from the left to the right, meaning that oxygen is more electronegative than nitrogen. So oxygen has once electrons more, it's more electronegative, and the resonance structure that has the negative charge on the oxygen is going to be more likely, more important than the resonance structure that has the negative charge on the nitrogen. So for this case, our major resonance structure would be this structure, and this would be the minor resonance structure. The reason you want to be able to recognize resonance and understand how to convert between resonance and drawing it's important to understand for two reasons. Again, I pointed this out. Resonance indicates that a molecule is stabilized because of its delocalized charge. Being able to resonate between these different forms means it is stable. So for example, carbonate anion is actually fairly stable despite that it has an overall charge of -2, and it's stable because of delocalization. So knowing that resonance is able to occur in a molecule will give you a hint about its reactivity to understand how stable it is. It'll also help you understand hidden points of reactivity on a molecule. So here is a resonance structure, the major contributor right here. This is going to be the main form that this molecule is in, but it can have resonance and form this minor contributor. And when you look at its minor contributor, you actually can see where some charge kind of lives, where the electrons move between. It shows you that this oxygen has a tendency to be a little bit more negative, and this carbon has a tendency to be a little bit more positive when you draw out the resonance structure. And that kind of shows you where reactivity can occur. You can see that electrons might move to the positive carbon. Remember, electrons are negative, so they're going to move to positive areas. So in a reaction where we're moving electrons, that carbon seems like a good spot. It's open for electrons to move to. Okay, so based on the rules we looked at just before, here's a question to get you thinking about resonance and the major and minor structures. So which of these resonance structures contributes more to the resonance hybrid? Would it be structure A or structure B? So in this case, I'm going to refer you to the rules that we talked about. Rules 5 and 6, mostly they're going to talk about which ones are contributing more. Rule 5 states that the molecule with the most covalent bonds is going to be the more major contributor. And rule 6 states that you want to have the least separation of charges, so the least number of formal charges. So that would be structure B. It's going to have both of those, follow both rules 5 and 6. It has 4 covalent bonds versus 3 in structure A. And it does not have any formal charges on any of its atoms, whereas structure A has a formal charge on carbon and a formal charge on oxygen. So this structure would be the major contributing structure in the resonance hybrid.